retirement plan and all that stuff. Okay, translations and transformations. So what we're going to be doing is taking some of those parent functions or those that library of functions that I had you go through and you're supposed to get all that information about. We're going to take those and we're going to shift them left, right, up, down. We're going to stretch them vertically, stretch them horizontally, compress them vertically, compress them horizontally. What we want to be able to do is look at an equation and be able to recognize what happened to it. Was it stretched, shrank, or compressed, or was it shifted up 3 units or left, right, down? We want to be able to look at that without having to graph it out of that. We do have the luxury of having the graphing calculator so we can kind of check some things, but it's good to be able to just look at something and be able to recognize, oh, I know that this is the same thing as an x squared function, but it's moved to the right 5 units. So you get an idea of where the picture's at, so you can visualize things. So that might change your range or your domain depending on how it's shifted out of that. So what we're going to be doing is talking about graphing techniques. We're not necessarily going to be graphing things. We're talking about graphing techniques. And what we're starting with is a original function, and we'll call that the parent function. Okay. Parent function would be something like y equals x squared or something, y equals the absolute value of x, something, like that. And there are some shifts that happen. And one thing that I want to kind of say before we even start, outside, think vertical. Inside, think horizontal. If you'll keep those two things in mind as we go through all of these different scenarios, if it happens on the outside of the parent function, it's happening vertically. It's a shift, it's a stretch vertically. If it happens on the inside of that function, then it's a horizontal move. Okay, outside is vertical, inside is horizontal. Okay, so if you'll keep those in mind, it'll kind of help you tie some of the things together as we go there. So a vertical shift. A vertical shift is taking something that starts here and just moving it up, or taking something that starts here and moving it down. That's all a vertical shift means. And what that looks like is you take the parent function and you add some number, and we'll use, k. We'll say k is an element of the real number system. So that just means k is a number. Okay. So we're adding or subtracting a number. So if k were negative, it would be, x squared minus 3. What that does is takes the squaring function, moves it down 3 units. If it were x squared plus 5, it would take that parabola and just move it from the origin and move it up 5 units. Right. That's all a vertical shift is. So if something is added to the outside of the parent function, it's a vertical shift up. If something is subtracted from on the outside of the parent function, it's a vertical shift down out of that. Okay. Horizontally, a horizontal shift happens on the inside because it's horizontal. So what's happening is you're taking some number and adding it on the inside. If you add on the inside, it's moving it left. If you subtract on the inside, it's moving it right. We're going to look at some examples of this in just a little while, but get some theory out of the way first. Okay, so adding on the inside moves left, subtracting on the inside moves right. Okay, adding on the outside moves up, subtracting on the outside moves down. Notice how it's kind of opposite. Normally you would think if you add on the inside, it would move it to the right, but it doesn't. It's the opposite of that. It's kind of like inside out. Kind of look out of that. So adding on the inside moves left, subtracting on the inside moves right. Okay. Next thing would be a vertical stretch. So my boys got silly putty in their stockings for Christmas. And how many people ever played with silly putty? You ever flatten it out and then get the newspaper or something and put it on there and then pull it back off and get the picture, the ink transfers to it. And then we always take that picture, and we always did it with Garfield when we were kids. And you take Garfield, and Garfield normally kind of round kind of guy, so you take that silly putty, you pull it like this, and it would make Garfield look skinnier, right? Okay, I'm looking for that. Anybody figures out how to do that with me? All right, so pull that vertical stretch of the silly putty made it look skinnier. So that's what happens to the graph, is it looks skinnier, but what's happening mathematically is you're taking some number a and multiplying it on the outside of the parent function. That number has to be greater than 1 to be a vertical stretch. Okay, vertical stretch, if you multiply by a larger number than 1, then it's going to stretch the graph vertically and make it look skinnier or taller out of that. Okay, if you multiply on the outside by some number that is a small fraction, so it means it's between 0 and 1, so like 1/2, 1/3, 7/8, anything like that. If you multiply by a small fraction, what happens to the answer? So say we multiply 10 by something less than 1. What happens to the 10? It shrinks. It gets smaller, right? Half of 10. If we multiply half times 10, we get 5. It makes it smaller. So that's a vertical compression, is what's the official name for that. You'll hear me say shrink or instead of compression a lot, because that's the wording that I learned it under. It shrinks the graph. It compresses it vertically. So if it looks the same. The only difference is the size of the number you're multiplying by. So if you took the x squared function, because we all know what a parabola looks like, if we took that and we multiplied it by 7, so 7x squared, it still looks like a parabola, but it's a lot skinnier and it gets taller faster. If we multiply x squared by 1/2, so 1/2 x squared, then it's still a parabola, but it looks wider because it pushes it down. Chris? Yeah, you can graph them with your calculator. You can graph the original and then graph where it's going. We get some examples. We'll look at that as well. But the idea here is that you would be able to recognize that by just glancing at the equation and seeing, oh, well, I know that takes this graph and does this to it. Let's do a horizontal stretch next. Again, things that are horizontal happen where on the parent function? Outside or inside? Inside. So we're going to multiply the inside by something. To be a horizontal stretch, you're going to pull that silly putty out this way, right? Garfield's going to get wider, and that's a horizontal stretch. For that to happen, you've got to multiply by some number that is between 0 and 1. A horizontal stretch, you multiply by a small number on the inside. Remember, it's the opposite of what the vertical is. Same way with the vertical shifts. If it was adding on vertical shift, you went up. If it was adding on horizontal shift, you went to the left instead of to the right. Okay, so it's the opposite of that. So a horizontal compression looks the same, but your number is bigger than 1. That's a horizontal. Now, graphically, it's hard to tell what happened to a graph if you don't have the equation. But what we're after here is being able to look at an equation and tell what's going to happen to the graph without actually having to graph it. Because let's just say, for example, if I multiplied the x squared function, if I multiplied on the inside by 1/2, what's 1/2 x squared. If I simplify that, you know, the way we do in algebra, what if I square 1/2, what do I get? 1/4 x squared, right? Well, this is a horizontal stretch, right? But this is a vertical compression. They look exactly the same graphically, but as an equation, their original equation looks like that. This original equation looks like that. So you've got to keep in mind, what does the original equation look like? And that's the one that I want to decide what's going on, what kind of translation or transformation is happening in the graph from the original. So sometimes, depending on what's going on, your vertical stretches and your horizontal compressions look a lot alike. Your vertical compressions and your horizontal stretches look a lot alike. They're not always matching up, but they do. They make the picture do the same thing. A vertical compression is going to squish it down, it's going to spread out when you squish it down, right? That silly putty, if there's a wad of it and you press down on it, it spreads out. Same thing happens with our functions for a vertical compression. Horizontal stretch, you're just pulling it instead of pushing it down. So it's the same. End result's the same though. All right. Next thing is a reflection.